Alright, in the Constraints tab, we have the opportunity to put further requirements on our solutions. And I should take a moment to talk about why the language is a little bit different here. So we're looking at optimized solutions here. We're not running a simulation. This is an optimization. It looks for the best solution given a number of different parameters. That's different than what we did in the facilities section. We basically gave it a set of parameters. We said, these are the conditions of the buildings. Now tell us what the energy usage would be. And that was done in Energy Plus. Here, we're using an optimization to say, we have these loads, this energy load, heating, cooling, electric load. Now for the baseline, we're also saying we know the set of equipment that exists. And so we enter that information in here in the Equipment and Measures tab. When we get to the additional alternatives, we're going to enter even more equipment. We're going to potentially enter new boilers for the centralized equipment. We might enter some cogeneration equipment. We'd say you could potentially, this solution could include some cogeneration equipment. It could include some photovoltaic cells, some solar cells. There could be a wind turbine. We'd allow it to look at all these different technologies, and then we'd constrain the solution. We're always going to be looking for the lowest cost solution on a life cycle basis, but we can look at solutions that include other types of equipment, and that's where this tool is really powerful. So within this constraints section, we can put on additional constraints to our alternative. Now in the baseline, we're not really going to end up constraining it because this is the as-is solution. But looking forward to the alternatives, and we'll hit this again at the time, but this is a good time to introduce it, we could do something like increase the critical electric maximum load. And what that means is we could say, for example, this group of buildings must always have access to at least 5 megawatts of electrical capacity in addition to the grid. So if the electric grid goes down, we could run at least 5 megawatts worth of our loads. There may be some critical loads, some critical infrastructure, and this is where we would put that requirement. So what does that really mean? What it means is that from the equipment in that alternative, not for the baseline because we already know what's available there, it could select from the equipment in that list to meet this requirement. So it may select decentralized boilers, decentralized chillers, and then a bunch of distributed diesel generators. That technology would exist in the equipment list. It would be available to be used in the event of a power outage, and we would have the installation costs and the maintenance costs associated with that equipment. Or, if it's a centralized group of buildings, we might also have engines or turbines in the central plant that could be used for cogeneration to provide both power and heat, and that would also be compared then to the decentralized solution. So using the optimization, we can look at lots of different types of total system architectures and determine the most cost-effective way to meet those goals. So we could enter that goal here, and there are a number of other requirements we can put on the solution. Right now, this renewable target has been disabled, but there are other ways to enact a renewable target. There's a maximum carbon footprint that we can add here and say this is the maximum amount of carbon that we want within a year for this solution. We can change the interest rate that will effectively further penalize high capital projects if you increase that interest rate. This is an important one to look at here, this net metering requirement. So here we can say whether or not net metering is allowed. And what that means is, is it possible within this group of buildings to export more electricity at any given time than we're consuming, and then push the rest off either to other buildings or across the fence out to the greater grid? Can we do that or not? There are some locations where we're looking at the whole installation, and if we provided too much electricity, we don't have an agreement with the utility provider. That's just not going to be an acceptable thing to do, and so it is not allowed. In other locations, this might be either it's acceptable that this installation, we can provide this agreement with the utility company to do net metering, or it's a relatively small portion of the base and the additional electricity would just be used by other buildings on the installation. It would never make its way out to a total net production for the installation. So in those situations, net metering will be allowed. And it makes a big difference in the type of solutions that we can find. There are many times where we would produce locally a little more energy than we consume for a few hours a year, and whether or not that's acceptable can greatly impact the economics of that system. All right, moving on, there are some additional requirements you can put on. The maximum investment cost here, you can see it's been set very high, again, just arbitrarily large, so that it doesn't constrain most solutions, but there are times when this becomes very important. There was a project we were working on not too long ago where a boiler went out for a central plant, and they wanted to know what they should replace it with. Should they just go ahead and replace it with another boiler, or should they look at cogeneration? Now, the only constraint was they had a limited budget. I think for this project it was somewhere in the order of $3.5 to $4 million. And there were only a few technologies that we could get in within that budget. So they said basically we could go either route for the technology as long as we can be below this budget, this absolute cost. So it didn't matter if we found a solution that was going to cost $6 million and have a really good life cycle cost that was much lower than their current situation. That didn't make any difference. It had to be below this price point. And so that's where this type of constraint can be very useful. If you put the constraint in here that the solution has to be below a set amount of money, say $5 million, then that will mean that only solutions that meet that and are the lowest total life cycle cost will be selected. All right, the maximum source energy here, again set arbitrarily high at first. You can adjust this. What we commonly do is we'll get through the base case. We'll have the future solution, the base case being the future case. We can compare that to our alternatives, and we might take the source energy numbers from the base case and decrease those by some set amount, maybe decrease them by 30%. If we were on some kind of glide path, we wanted to make a 30% reduction by some future date, we could decrease that source energy, say from 100,000 megawatt hours or something per year down to 70,000 megawatt hours per year. And that would mean that our solution is going to meet that maximum source energy. So it will reduce the source energy by 30% and give us the lowest cost solution that meets that requirement. So it may not be as low cost as not meeting any requirement, as just going about the status quo and using all standard equipment, but it'll at least show us what it would cost to reduce our energy to that level. All right, maximum combustibles is going to be related to the waste to energy systems that we can take a look at. Here we're just going to set the maximum amount that could be found either on the installation or in the nearby area. This is a way to constrain basically the potential for waste to energy. And then we have the redundancy types here. So this again could take a minute to explain. I would say the additional capacity, so there's two types here. We've got additional capacity and redundancy, and these are both related to central plant operations. So on the heating side, it's common to have some amount of heating redundancy. We could have some multiplier of the peak, so we could say something like 1.2 or 20% more heating capacity than our peak. That would be just for to determine approximate capacities that would cover all of our energy usage, but not really designing a system. If we wanted to get closer to a design, kind of a pre-engineering level, we could click N+1 redundancy, which would mean we could meet our peak when all of our equipment was being used, but our largest piece had failed or was down for some reason. So that's generally called N+1 redundancy. And so this is something that's a little bit closer to sizing the equipment. We can actually choose from that equipment list different sizes so that we could meet this requirement for the lowest cost. And then similarly on the cooling side, More so just for central plants, not so much, on distributed equipment. We're going to size it appropriately for a single unit usually. If it's a larger building, there may be multiple units, but that's a different type of design decision. This is looking at larger scale systems. So here we can toggle between these. Using the N+1 redundancy does take a little bit more computation time, and it's not really needed for a planning level analysis. So we're going to stick back down here to additional capacity. And because this is the baseline, again, we don't want to put any constraints on the baseline. We want to run it as is. We can further constrain our additional alternatives going forward. So we didn't really change anything here, but we are going to save it anyway. Just save it the way it is. And it's going to turn all of those indicators green. And we'll click to continue. All right, in the optimization page, we're going to click to pull this down. This is a very similar page to the simulation page back in the facility load section. Here we can click this out. We only have one alternative right now, the baseline. Later on, we're going to see many more showing up here down below. And we have our two building clusters, centralized buildings and decentralized buildings. We've got very similar icons here. We can reset these if they'd already run, reset our runs. We're just running through the optimization here. We're going to be solving. I'm going to go ahead and click Optimize Study Plan Clusters. You see this icon here. It's the same icon, but a smaller size for the individual clusters. You can click these individually to solve them on their own, or you can just click the master button to do them all at once. Now it'll take a moment and then update to show us the status. When we only have two, it shouldn't take very long. They will initially go into a queue and then should very quickly start running. You can click this refresh button to see an update on the status. So now they're both running. For baseline tests, there's very little computation that needs to be done. It should be a very fast run. Go ahead and click again. Usually this takes less than 30 seconds until the optimization is completed for the baseline. When we get to the alternatives, it will take a few more minutes, something closer to the amount of time you would see for the facilities running. We'll click again. Now we see the status has changed. It's gone to polling. That means that the optimization is done. It's completed. That information is being parsed out and brought back to the interface so we can view it in the results. We can refresh again. This does take a moment as well.